Hello, today we are going to be taking a look at limits. First of all, what are limits? Limits are a way of examining what the behavior of a function is at its y coordinate as x approaches a specific coordinate. The notation for limits is as detailed here. We always need this lim, short for limit, and then underneath that it is going to have x, which is the variable we're going to be looking at here. And this arrow means approaches. And there's always going to be a value a. Now, that can be a constant value. It can be an infinity, a negative infinity, and we can approach from different directions, which we will take a look at in a minute. You always need a function. You cannot just say limit as x approaches 4 and then go on with your life. You need to have your f of x, your g of x, whatever function we are taking the limit of here. And our output for this, our limit, is always going to be equal to some value. And the question that we want to ask is here, what is the y value getting closer to? I want to talk a little bit more notation, and then we'll look at some examples in practice. Now, we have some one-sided limits and two-sided limits, and they are exactly as they sound. One-sided limits are where we're approaching x from a certain direction. So this first one is our limit as x approaches a. This is from the left, shown by this little negative sign in the exponent for a. That means that our one-sided limit here, where x approaches a with a little positive in the exponent, is going to be from the right. Sometimes our one-sided limits as x approaches a value are going to be equal from the left and from the right. Sometimes they will not be. And we'll look at the different cases in a minute. Then two-sided limits, you're just going to have limit as x approaches a, nothing in the exponent. So in order for a two-sided limit to exist, we need both one-sided limits they have to be equal. Now, all of these you would have an f of x after. I just wanted to talk about notation here. Let's look at a few examples on a function that is continuous. Our first one on the left here, the green, is saying our limit, and I did forget to write the f of x in, the limit of f of x as x approaches negative 4, this is from the right, which is what the positive exponent is going to say, means that we find negative 4 on our x-coordinate, and we're going to follow the function as x approaches negative 4 from the right. So it's not approaching the right, it's coming from the right and moving towards negative 4 on the x-axis. So our answer to this, our output for these limits, is going to be what the y-coordinate is doing. So here, the y-coordinate is going to be 2 as x approaches negative 4 from the right. So our y-coordinate is 2, and that's the important part for the limits. Now, with a function such as this one where it's continuous, so we can draw the entire function without picking up our pencil, and there's no discontinuities. So there's no vertical asymptotes, there's no holes, there's no jump discontinuities. Our limits are pretty straightforward, so this is a great example to start out with. If we are looking at this side, however, our limit as x approaches negative 5 of f of x, this is a two-sided limit. So that means we need to take a look at what's happening as x approaches 5, negative 5, from both sides. So as x approaches -5 from the right, and the thing is, we're following along with the function. Think like you're tracing the function with your finger, or imagine like a little person walking along the function. Where would they get to? Where would your finger get to if you're moving it along the function, tracing it? As x approaches -5 from the right, the y-coordinate is approaching 4. As x approaches -5 from the left, again, we're following the function, that y-coordinate is also 4. Since our one-sided limits are equal, the two-sided limit is going to be whatever that value is, so it's going to be 4, which is the y-coordinate of that point. Now, the function exists at f of 5, like in this case, f of 5 is also equal to 4, but it does not need to be for the limit to be the same. So let's look at some examples here. We've got a graph. F of 0, f of 2, and f of 3, these are just looking at what the y-coordinates of the function are at these points. So f of 0, we take a look at x equals 0, go see and find the function, and since this is an open circle, this does not exist. The function is undefined at that value. F of 2, we take a look at x equals 2, and we see that the y-coordinate is equal to 0. All we're doing here, finding the y-coordinate, and then we'll go from there. F of 3, we take a look at the function, and the filled-in circle is at that y-coordinate at 3. Now, the reason we're doing these is to help differentiate between what the function is doing at a specific value, so just finding the y-coordinate, and determining what the limits are. So for example, we look here, the limit as x approaches 0 from the left, and that's what that little negative exponent is. So we find x approaching 0 from the left, and we take a look at what the y-coordinates of the function are doing. So the y-coordinates just keep going down and down and down. As x approaches 0 from the left, the y-coordinates keep going down, down, down. It's going to be a vertical asymptote at the y-axis. So this is going to be -infinity for that value. We had said earlier that limits could be infinity or -infinity, and that's if this happens where the function just keeps decreasing without bound. Now, this two-sided limit as x approaches 0, we would need the one-sided limits to be equal. But as we look at x approaching 0 from the right, that would be equal to 2, because if we follow along this function as x approaches 0 from the right, we would be going to 2. It does not matter that the function does not exist at x equals 0. Does not matter that there's a hole there. That one-sided limit would still be 2. Think about limits almost as directions. So the directions take you to a place. And if that place you look up, you're supposed to find the building you were looking for, and there's a giant hole in the ground, your directions are still taking you to that building. It does not matter that it has disappeared. So this limit does not exist. Now, let's take a look at these same values with 3. So our limit as x approaches 3 from the right, that's what f is talking about here. Limit as x approaches 3 from the right. So we find the function. We're approaching from the right. So we follow along. And the function would be going towards this y value of 2. So that one-sided limit as x approaches 3 from the right is going to be equal to 2. It does not matter that f of 3 is 3 because the directions that the limit is giving you are taking you to that point of 3, 2, even though it's a removable discontinuity. Then we take a look at our two-sided limit as x approaches 3. As x approaches 3 from the right, we said the value was 2. Our limit as x approaches 3 from the left is going to be equal to 1. Since those are not equal, the limit does not exist. You can also think of two-sided limits as you and your friend are coming to a place from different directions, and even if there's a hole in the sidewalk where you were supposed to meet, if you can reach over and shake hands over that hole, then, like if there's a removable discontinuity but your one-sided limits are equal, then that two-sided limit exists. If you can't, the limit does not exist there. Now, when we look at a limit as x approaches infinity or negative infinity, this is going to be the end behavior of a function. So in this case, as x approaches negative infinity of f of x, that function is approaching that horizontal asymptote at 1. Let's take a look at another one together. So here, let's see what color is going to be easily seen here. I think red will work. So let's start out with this f of 3. I know it's letter D, but I just want to make sure that we start with that. F of 3 is just a dot right here. So f of 3 is equal to, if this is 4, 3, 2, 1, 0. This is not the best labeled graph, but it will work for our purposes now. So f of 3 is equal to that y-coordinate at 1. Let's take a look at our two-sided limits then for a and b. Our limit as x approaches 3 from the left, so we're coming from the left, following along the function, and then looking at what the y-coordinates are doing. And our y-coordinates keep going down, they keep decreasing without bound, so this one-sided limit is going to be negative infinity. The same thing is happening as x is approaching 3 from the right, so that is also going to be negative infinity. In that case, our two-sided limit as x approaches 3 of f of x is also going to be negative infinity because our two one-sided limits are equal. Now let's just take a look at our end behavior for e and f. Our limit as x approaches negative infinity, we're following the function, and it looks like there is a horizontal asymptote here at 1. And then a similar thing is going to happen at our other end. Our limit as x approaches infinity, we're following along the function, and it is going to have a horizontal asymptote at 2. We've got one more we'll take a look at. So that one was quick. And here we've got looking at this at f of 0. So here's the origin there. So f of 0, there's this filled in circle, this dot. The function is equal to negative 2. Our one-sided limits as x approaches 0 from the left, it's going to be 1 because that's what our y-coordinate would be approaching. It does not matter that there is a removable discontinuity, that this is an open circle. Does not matter. The limit is still taking you to 1. Our limit as x approaches 0 from the right, our other one-sided limit here, this function just keeps decreasing without bound, so it's going to be negative infinity. That means our two-sided limit does not exist because our one-sided limits are not equal. Our end behavior, our limit as x approaches negative infinity, this function looks like it just, if we approach negative infinity, the y values just keep increasing. So we're going to say infinity. And the same thing is going to happen as x approaches infinity. Now, what I'd like you to do is try these out on your own. Thank you for watching.